feel that there is a gap between what we have to learn and what we have to teach. And over the course of time, I've understood that there is always that gap that needs to be filled. And right now, this podcast is going to cover all the bright insights that you are going to need when you're supposed to be working on the hardware inferences. And right now, there is a lot of hype and hope beyond what ML can give also. So right now, let's just demystify all these things that we are supposed to learn and supposed to unlearn over the course of time with Suhas sir. Thank you so much, sir, for giving me this podcast.
Yeah, thank you, Vishwas, for your initiative, and I'm very glad to be part of your podcast.
Yeah, let's just start with your journey as a student and a professional. How was it all about? Like, how did it begin, and what were your dreams over a course of time?
So basically, like, I was also just a normal next door boy who I wanted to do something on the engineering side, everything. So I was basically got interested to electronics during my 11th and 12th when I studied about all these basic gates like AND gate, OR gate, universal gates, all those things. That's when when the interest to electronics actually started. Then I gradually, like when I came to the engineering, I just took electronics and communication only mainly based for the broader scope it had. You're not just restricted on the software side like the computer science. For the hard, you also know you can work on the hardware and you can build your knowledge on that. That was the main motivation to get in with the electronics and communication engineering. And here, like after I joined, like electronics always fascinated me. It's not just that p-type semiconductor, n-type or anything. It's just the gates, what it can actually do. Like electronics as a whole, it fascinated me. The Silicon Valley, or being born and brought up in Bangalore, where you see all the silicon companies being located, that was also one of the reason behind. And seeing my other seniors worked in different silicon companies was also one of the reason. And then the iPods, mainly the iPod was the one which fascinated me, where you can store billions of songs in a small devices, where everything was so miniaturized and it can do a large amount of task. So this was the main motivation of learning something with respect to or starting with respect to the electronics and communication engineering. So later on, like after studying this, VLSI was something which I got interested in. Initially, the digital electronics was something which I was very fascinated about, like where everything is with respect to ones and zeros, not like a continuous time value like an analog. So you have a lesser amount of parameters to worry about in digital rather than when compared to analog. So even though analog is very important for every aspects of electronics, digital was something which I was very fascinated about. And then I think, if I remember correctly, it was in the fourth semester or fifth semester, I think it's in fourth semester, where I learned this Verilog programming, where you do where you build the complete architecture of the processor in the Verilog, you do the synthesis and then dump it on an FPGA and see the results. That was the initial part. And then the actual VLSI, I think I studied in fifth semester engineering, where you learn about the PMOS, the NMOS, then the CMOS completely, and then the different bus architectures, all of them. Then in sixth and seventh semester, I did one was the microelectronics, which that Adel Cedra, that was the book which actually motivated and improved more of my knowledge on the VLSI design. And then the VLSI lab, of course, like the cadence thing which I worked during those. I mean, I didn't do anything very big. It was just building certain small inverters or all those things. This is how the basic knowledge on VLSI for me started. And then the master's was mainly on the VLSI design and embedded system. Embedded system was just a part which I wasn't much interested on, but the VLSI was mainly on the thing. Then as it went, then I got into ISRO also, then where I mainly worked on the genetic algorithms, where I built the genetic algorithms, dumped on the Spartan 3 FPGA series. Then I could test it on the real applications for the spacecrafts and all, and we can put it into this. And then for the other interstellar missions, all of them. This is how the interest kept on increasing for me in VLSI. And then the one journal which I published it in IET Journal of Research, I mean, using the Taylor and Francis publication there, that was where I wrote about the Heskalon genetic algorithm. So that is when I completely did the entire computer architecture for the spacecraft to employ the genetic algorithms to check if all the processor are working fine on the onboard computers of the spacecraft, even if it has escaped the Kármán's line or the geostationary orbit. So this is how the interest sparked in me. During the doctorate, I just wanted to do something on the ADCs and the DAC, or high-speed DAC, or the pipeline ADC, or the Sigma Delta, or something. I wanted to work. Mainly, I wanted to go through the analog. But at that time, there was a large amount of innovations happened in 2017 and 2018 in the technology era. So the two things: one was the Apple released the iPhone X, and Google had its own TPU, so to store their Google Photos Drive application, and that involved machine learning. That is when something called machine learning concept came into me. And then I did almost 1 month to 3 months of complete study, right, starting from the basic, like what is machine learning, what is artificial intelligence, why is deep learning so important, what is deep neural networks, how is it aiding our actual iPhones, like how is it like doing all this so much of complex task. And then it actually, the machine learning algorithms had simpler maths, like it had the concepts of linear algebra, the convolution, simple pooling, where you take the maximum out of certain sets. So iPhone 10 series was one which actually fascinated me about machine learning. So you could unlock a phone just without using your fingerprint, just with your face it could unlock. So there involved a large amount of deep neural networks involved into that, where the processor has to do large amount of calculation to be sure that it was your face that is there, and then only it could unlock the phone. So iPhone 10 series was one of the innovations that sparked my interest in machine learning. And Google Photos, because always you go visit the parties, you store a large amount of photos, the one which could not fit into your phone, everything was going into the Google Photos automatically on the cloud. So to store them and to remove all the clutters, like the screenshots, and map them according to your faces, everything tensor processing unit was doing at the background, which was a 2.25 millimeter cross 25 millimeter chip was doing all the things, which I was doing all the machine learning calculations. So these were the two products which actually it made me interest to do the PhD in machine learning and deep neural networks. At the same time, there were some academic institutions like MIT and Stanford were also mainly working on that. So MIT had their own processor called Iris. Stanford had EIE, and one of the another university which was near to me, it's called ETH Zurich, which is in Switzerland. They had their own origami papers which was published. So all these papers in ISCCC and JSSCC were the ones which I read throughout the 1 to 3 months initially, along with the basic concepts of machine learning, which made me believe that machine learning processors are the ones which I can work on, and I'm actually good in that because I had good background in the maths. And also it was not complicated. It didn't involve anything like field theory thing where you do all the partial differentiation, which is very tough on the hardware. It was just a very simple maths was involved for the hardware. So I thought it can be done. And even though the complexity was not much, but the application level was huge. You can apply it anywhere. So it had a huge boom. So, and I was fortunate that I was born, I started my PhD in this era where I had a topic to work on, and that aided to my doctorate degree. So this is how it actually started. Then I worked on it. So I worked on to reduce the power thing and the memory requirement on the FPGAs as well as on the ASIC side for the machine learning, using the top tier models like AlexNet, SqueezeNet, EfficientNet, all of them. And one I worked with the Fraunhofer HHI in Germany, where we work mainly to reduce the computation requirement, and to fit the larger models like Facebook, all of them into to reduce the overall size requirement on in App Store or where, and do the larger amount of processing with lesser amount of resource consumption. So these were the few things I worked upon. Now this inference is starting to fade because the peak has ended. Now there is something more is happening, like integration of RISC-V into the deep neural network accelerating, or some other spiking neural network which is already developed by Intel is taking place, or more innovations are happening on the memory side where Micron is working upon, or still A15 Bionic chip is coming in the iPhone 13 series. So the innovations are happening, but new concepts are coming in. So I came in the early part of the wave. So now it is gradually decreasing, but yeah, so this was some of the basic things why I came into this, and this is the background on how I landed up here.
Yeah, I just wanted to know what are the challenges today in ML inference, because not about that, leaving the part of bringing such complex architecture, I just wanted to know what are the challenges today?
So challenges means, like, first we have to agree that machine learning models are huge. So if you stream a 1080 pixel cross 720 pixel or still higher than that, you can assume so much amount of data is there. You need to store them. So first and the foremost challenges is memory. I think memory powerhouses like Micron are working extensively on aiding the AI infrastructure and all. So memory is the first bottleneck. Then again, the resource requirement. If you are on the ASIC, you don't have it, but still the aspect ratio on the chips will increase. On the FPGA, you're already resource constrained if you're not working on the big FPGAs and doing it. So you should be very smart in the architecture, loading of the data path. And of course, again, since you are handling so much of computations and data, power is the major bottleneck, and the speed is also something which is very important. So since you are doing so many things, it involves larger amount of floor plan, larger area, larger amount of routing tracks, everything. So setup and hold timing becomes very crucial for the chips to work properly. So timing, power, again PPA, whatever we call it in the technological semiconductor terms, performance, power, and area. All the three factors plays a very important role, and maintaining all the three of them is always a challenging task as a machine learning inference designer or a scientist.
Over a course of time, what do you think about the inference hardware that we are talking about?
Inference hardware is just like you do all the training, you just create the trained data, like for the images, the weights, everything, then create the hardware which can do the processing at a bottle of just in a matter of seconds, because the processors usually operate at certain megahertz to certain range of gigahertz. So you do a lot of tasks, like a lot of implementation. Make sure that you have a proper memory, like the SRAMs. Like you can't build an entire chip with an SRAM, but you ensure you need to do the balancing between the SRAMs, again moving between the DDRs and the SRAM, and then the memory accessing should be taken care of, and then the data path, then doing the computation. You should be very smart, because the main heart of the machine learning inference computation is the MAC unit. So you should be very careful, because multiplication operation consumes more resources than the addition. You should know what to do with MAC and what to do, when to do addition and when to do multiplication, and then you should be careful on doing the non-linearity issues, and then again putting the data back to the memory and doing the loop ping pong back to the smaller scratch pad memories in the PE array and doing the computation. So the entire inference revolves around memory, computation, and loading the data back to the memory and repeating the process again. So these are the few basic concepts behind that, behind the inference.
But what about the architecture? Because we still have the RISC and the CISC, which makes a compute over a course of time. And models that we are building is not that compatible, right? Even when you take Onyx is also doing pretty great in terms of inference, but on the performance aspect, I think probably architecture has to have a little bit more of maturity on the inference part. That's what I feel. But what do you feel about the architecture that we are trying to develop? Because day to day, you develop some or the other kind of an architecture where you have something to do with testing or something to do with some sort of an architecture. So what do you think about the architecture that we are seeing today?
So basically, like in terms of architecture, first we either go with the spatial or the temporal. Usually we take the spatial because of its efficiency and ease of doing the task. And moreover, with the risk or CISC, it doesn't matter. As I said, like now the risk file is getting integrated into the acceleration with its own set of instructions set to load, do the computation, etc. So the architecture, it doesn't matter. At this point, we should be only careful. As a machine learning inference, we just mainly take care of the amount of computations we need to perform, and then based on the specification, we design the amount of memory that is required. We can't do much more than the ones that are already defined by the foundry, especially on the memory side. So we should be very careful when determining the width and the depth of the memory, and then moving the data from the DDR back to the SRAMs, and then moving the data like using the FIFO concepts, and then moving the data inside the PE array, which is a MAC unit or the ACM unit, then doing the computation, and then moving it to the output array or the output memory. And all of this should perform at a certain amount of considerable speed. Like it can't perform like in kilohertz or something. It has to operate either at a higher range of megahertz to a lower range of gigahertz. So it has to be speed centric, because you need to perform a task. If you are operating at a lower speed and if your iPhone is taking like 2 hours after your face, then it's a junk, right? So you need to perform it very quickly like this and then get the output. So architecture wise, we mainly concentrate on the data path, how efficiently we can reduce the power, when to use the clock gating to reduce the unwanted dynamic power dissipation, and then we use large amount of clock gatings because to disable certain parts which is not operating, so that in order to save the power. And again, the area is the most complicated one, because machine learning models are huge. You can't store everything on chip. You need to store something off chip on the DDRs and then move it efficiently. So these are the concepts that come behind the architecture. Instruction set can be adjusted based on the requirements of the application. You can build your own instruction set and do it, and at what time, where should, like when to read, when to execute, and when to write. So you can define it for certain amount of nanoseconds, like how you need to do the data. But at this point, data path, dynamic power dissipation, and performance, the power, performance, and area are the three important concepts that needs to be taken for the architecture.
So I just wanted to ask you this one question, because your day-to-day aspects of any work, like anything that is more relevant to Verilog and things like that. But sometimes even VHDL also plays a huge role in what we saw as a deployment. So I wanted to know, what are the ways in which we can really tune the architecture of an accelerator? So we saw ASIC, we saw a bunch of FPGAs which can be configured. We saw a lot of things, but I want to understand, what is it all about when you're fine tuning the performance of an accelerator? And actually, you can also talk regarding pains and the gains of adding an accelerator to a process which is already running fine.
Accelerator means it's just a term that is given for a machine learning processor. You can even call it as a machine learning processor. Accelerator means it is something that is used to accelerate a particular task. Here we are accelerating the machine learning task so that everything is performed quickly, and so that it can aid an application like an iPhone 10, 11, 12 series models, or whatever the Android series it is coming. So it's just that we accelerate and we perform it at a particular speed and frequency and do the particular operation at that particular time. That's why we meant acceleration. And the architecture, as I said in the previous question, the architecture, again, it is dependent on the models that you are using for inference. It can be any models, right? It can be an AlexNet or a SqueezeNet or an EfficientNet or the mobile nets, especially designed for the mobile application. So it's a large topic, and you cannot say one architecture is suitable for all the applications. So it depends. So for accelerator, it's different applications, that it's different architectures.
Yeah, but I wanted to know, because a lot of times when we are working on some aspects like power, probably we think of something as federated. Like there's a concept called as federated learning, which always pops up and says, hey, you just give me tons and tons of model, I'm going to stitch it up and make some decision. But when you think of RTL development, which is like completely a mess, which is nowhere related to whatever we might be talking, but we are supposed to architect over it. So what do you think about the RTL development that is happening today? Because most of the DFT aspects also come up here, and a lot of DFT engineers also talk with you. And what is it all about when you are stitching something for such kind of architecture, like hefty loads?
So basically, like when it comes to RTL, first you need to know your specification. So you need to know what models you are inferencing, what kind of architecture you want to build, then only it can be done. So first you need to know the specifications, how much memory is required, everything. Then you first, on the RTL development, you first code up the memory so that you can store the image and the weight data. So you there in the memory you have the SRAM and the DRAM. DRAM is mainly of the DDRs, and SRAM is the on-chip SRAM, which is in certain megabytes or maximum certain kilobytes. So in terms of the ASIC, we can talk, because that is the actual chip that goes in. So every foundry gives you a certain memory models where you can do the you can recode it and build it according to your requirement, but that would be size restricted. So first you need to know how much you can handle the data, so that your chip doesn't overshoot the aspect ratio. First you define the memory, the size, and then try to load the data into the memory using your RTL, and it's a simple RTL SRAM how you want to do, with all the controls and the FSMs involved, like the Moore or the Mealy state machines involved. You do all the FSMs that is involved, you load the data onto the memory. Once you have loaded the data, then you should be very smart enough to define a FIFO unit, because if all the data is not filling, you need to do the memory loading parallelly and computation also in parallel to avoid the total inference time. So then in the RTL time, then you need to concentrate on the FIFO development, so that one data, if it is fetched, that data needs to be filled back at the last row. So you do the FIFO development. After doing the FIFO development, then you put all the data into the computation unit, which is called the ALU before. Now it's called as the processing unit in machine learning. You do all the processings like the MAC unit, like the multiplication, accumulation, everything. Or sometimes like my fantastic IC4 papers, where I did the ACM approach to avoid the power consumption. So I use the distributed law of arithmetic. So to reduce the power consumption, you can use the ACM principle to do the operation, and then do the pooling and the non-linearity, which is the ReLU. And then those are the simple arithmetic operations you do. And finally, you load the data back to the memory, and then again load it to the SRAM. And before this thing, you need to build something called an AXI master. I think you know what is an AXI means, like which is already using this concept of taking the data with respect to the read address, that data, and moving it into the SRAM and loading the data. So so basically you do all these concepts with respect to RTL AXI master. You need to write it on your own, because the AXI slave is from the DDR side. Then you need to have your own on-chip SRAM and for the image, weight, bias, everything. Then you have your own FIFO unit, which is again defined. FIFO is again a different concept, where you have a read FIFO and a write FIFO, where you have the different buffers involved, read pointer, gray coding involved inside that. And then you do the computation, which does the MAC implementation. From there you store the data and again move it back to the AXI master. So these are the complete concepts, or the basic concepts, that are involved in the inference of a machine learning processor. So it involves all these things, and everything needs to be coded RTL. And if you're coding something in RTL, as a person who have worked on this, from my experience, I can recommend that it is better if a designer does it in Verilog rather than VHDL. VHDL is not so suitable, People does that, but it's not recommended. So it's always better to use either the system Verilog or the Verilog to build all these models in RTL.
But what about the benchmarks that we are coming up today? Because a lot of benchmarks that we are talking about is basically something which has to deal with a trade-off. Either you want power, then have a trade-off of performance. If you want performance, have a trade-off of anything that is inferred right now. So I want to understand, like, what is it all about benchmarks today that we are talking about?
So benchmarks means basically it can be like, as I said, power, performance, and area. So higher the speed, higher will be the power, that according to the normal definition of dynamic power dissipation that is known, where the power is directly proportional to the frequency. As the frequency increases, the power increases. So we should be smart enough in using the clock gates, especially to disable the gates when to not to perform the operation, where you can reduce certain amount of dynamic power consumption on that. And performance wise, yes, as I said before, you don't want your iPhone to unlock after 2 minutes after seeing your face. So you need to maintain the clock frequency also, like in a higher range of megahertz to the lower range of gigahertz, and then do the inference operation. So as a designer, it's always like you need to handle all the three trade-offs to get a design. So most of my designs had a total area of 1.2 millimeter cross 1.2 millimeter, which is not small, but also it's not big. It's a medium size. So the power consumption was not also very less. It was around 700 to 800 milliwatt of power was getting consumed with a 22 nanometer process node. So the trade-offs are tough to handle for an engineer or a scientist, but there are workarounds, like in order to improve the power or the performance, you can replace the MAC with the ACM to avoid the unwanted multiplication. Floating point unit you can't do. You can convert the floating point numbers to fixed point numbers, as I have explained in the Fantastic IC4 paper or in the Fantastic IC4 journal. So you can do that, or in the other way, you can completely convert it into fixed point and then do the rest of the operation to save power and energy. And ReLU is something which is always doing the power saving, but it's a very minor unit in the design. So all these small concepts like clock gating or latching or using the multiplexers to select the data rather than keeping all the ports running. These are some of the concepts where you can use to improve the power. Performance, you need to operate at a certain frequency, and you should be smart enough to handle the buffers, remove the buffers to maintain the desired speed. And area is something, again, it depends on the application. If you want to have a powerful neural network, you can't have an area around 100 micrometers across 100 micrometer. You need to be in certain millimeter, which is still fine, because all the chips in the phone are in a very big millimeter itself. So that is fine, but you cannot cross the aspect ratio. So all these things, it needs to be balanced as a designer. Sometimes it can be done, sometimes it cannot, but that's the way it is for now.
That's true. That's true. Because most of the time when we are building models, when we are architecting a solution which makes some inference, there is a lot of trade-offs like clock attack, voltage attacks. There are hundreds of things which comes up. Like probably there can be an untuned model, like a file format can be thrown in, and probably there is no inference which is happening because of that. I think, yeah, you covered a lot, sir. Thank you so much. But I want to ask you some learning path, because most of the time we want to learn something and begin, right? So I just want you to give some learning path, any books, tips and tricks, anything that you want to say.
Okay, for books, for machine learning, there are tons of materials that are available on the internet. Google search, if you want to understand the concepts between deep neural networks, the calculations, the convolutions, the pooling, either the max or the average pooling, or the basic history behind everything is available on the internet. For RTL coding, Verilog, I suggest Nazia M. Bothra's, which is HTL programming book, or the Peter J. Ashenden, Digital Design of Verilog, those books, because I always recommend Verilog rather than VHDL. VHDL is too boring, and also it is very type centric, which is not efficient for something for a larger applications. I know industry uses VHDL, it's only very long. So coming to the physical design concept, like of building the chip, like you need to do the RTL, then you need to do the synthesis. There are so many lectures from TU Berlin, ETH Zurich, Stanford, Harvard, not Harvard, MIT or somewhere. Few of the lectures which I gave in TU Berlin is available in the TU Berlin repository, where I gave about the complete synthesis, floor planning, physical, then placement, clock tree synthesis, routing, physical design verification, then STA concepts, and dynamic power and rail concepts, and for dynamic power and static and dynamic power consumption, static and dynamic rail analysis, all of them. So these are the books. So the book lectures are, as I said, there are tons of lectures from TU Berlin, all of them. You can look into that. If not, you can also look into some of the books, like from the synopsis, Ananta P. Chandrasekharan's Introduction to Physical Design, all of them. See, these are the ones that helps you to build the chip. So what I recommend is, like, if you have some basic work experience before on working on some of the chips, like in any of the semiconductor majors like Micron, Intel, Qualcomm, or Google, Apple, somewhere, if you have worked on certain physical design concepts and then building a machine learning processes, especially on your PhD, will help you a lot. I didn't have that background. So for that, I had to work before on some of the like DDS processors, everything. So basically, like, to learn this chip related one, first, it's better if you had a work experience before in the industries which I said. If not, you can enter into a PhD where you work on only on the physical design of the processor, not on the machine learning side. Build the chips like the basic digital design chips, and then do the machine learning processing is also a fine thing. But it's not a one-day thing or 1 year thing. It will take around 3 to 5 years to learn all these concepts and get a master on that. First, we should be patient on this thing, because it's not so easy, because the concepts are too vague, and then we can get into this topic. So first, background, interest, and then patience. These are the 3 factors that will help you get a machine learning processor or any chip or anything in the industry.
Yeah, sure. I think, thank you so much, sir. Thank you so much for this podcast. Yeah, we got a lot of insights from today's podcast. Yeah.
Thank you, Suhas, for your time. Thank you so much. I hope I answered your questions and it was of a help. Let me know if you have anything further, if you want to talk about or something. But this is something, again, as I said, it's too much in vague. If we start to explain one concept, it will take almost 3 to 4 hours for one to explain this. These are something which I have explained in brief. If you want to know more, again, I had told you before also that you can just type my name in IEEE Explorer, or in Google, you'll get all the list of the papers I have written there, and then you can just go through it. And again, I am more of an inference rather than on the training. I got the train data from the different colleagues of mine during my doctorate, and so training itself is a different concept, which is more time consuming, but it's not as complicated as the inference, because training mainly involves floating point operations, and you can do everything more quickly than the inference. But whatever in this time I got, I have explained, or I tried to do it, and if you need something more, I'm very happy to get back to you.
Sure, sir. Sure. I think, thank you so much. Thank you so much.